let's go to the dosing. How ozone is dosed in systems nowadays? Well, there are, like, let's say, two very accepted ways. The first one is the side stream injection. So you have a certain side stream, part of your water you take out, you ozonate it, you inject a lot of ozone in it, and then you reintroduce the side stream in the mainstream. This is like a pipeline reactor, but you have different kinds of systems. That's one way, of course, many of you are familiar with it. The other way is bubble diffusion, FBD, fine bubble diffusion, are also a very well-known way. Huh? Well, of course, they are very different. And uh, we will now actually build up the story a bit more. And let's now do a similar run, but we will now be looking at a real plant. So for this, we will go to our colleague, Roberta Muyo, and she will be sharing her screen and do another demonstration for us.
Yes, thanks, Wim. So good afternoon to all the participants. In this lab demo, we'll be looking at a virtual full-scale plant. So it is, the layout is here. You can see it is a sequence of bubble columns, both current and counter current. So you have the influence here, then the flow enters the first bubble column, which is made by a small compartment. So the first compartment is called BC11 and is here at the top. Then the flow goes down to the second compartment and then to the third compartment, which is called BC13, in which the ozone is dosed via the diffusers. Then the flow goes to the second bubble column and so on till the effluent. So in this exercise, we will first dose a certain amount of ozone, a certain amount of gas flow in a single bubble column, in BC1. So for instance, we are dosing 1000 liters per minute in BC1. Let's see what is the effect in terms of ozone residual and in terms of bromate formation. So the simulation is finished and we can now take a look first at the ozone residual there. So here in this bar chart, you can see the concentration of each variable in each compartment. So here now we are looking at the ozone concentration from the influent then to the first compartment of the first bubble column, second compartment, third compartment, and then the flow goes on to the other bubble. Is that the ozone concentration, the ozone residual, is higher in the third compartment of the first bubble column, where we are dosing ozone. Then there is some ozone residual downstream and also some ozone residual upstream in the upper compartment of the BC1. Now, if we look at the bromate concentration, we see that there is a spike of bromate formation where the ozone residual are highest. And also there is a little bromate formation downstream and a little formation of bromate upstream. But downstream in our installation, there is no ozone residual, so no more bromate formation will occur. And in the effluent, we have, in this case, 16.8 micrograms per liter. Now let's see what happens if we split the dose in two bubble columns. So now we are dosing the same amount of ozone, the same amount of gas flow in BC1 and in BC3. Now let's see what happens in terms of ozone residual and especially in terms of bromate formation. Now the simulation takes a few times to update. In the meantime, we can also see that we can check a lot of plant-wide variables, so we can monitor and time dynamically the ozone transfer in each single bubble columns, the ozone ratio respect to the DOC, the overall dose, and so on. And now we can go back to the bar chart. The results are uploaded. Now we see that the highest ozone residual occurs in the third bubble column. So in here, close to the diffuser, there is some ozone downstream in the next bubble column and some ozone upstream. There is also some ozone in BC1. So what we did now, splitting the dose in two bubble columns, is letting the ozone react first with the organic matrix, with the organic compounds, the water metric in the first bubble column, and in this way we allow ozone we increase ozone lifetime downstream. And in terms of bromate formation, in this way we are controlling the bromate formation in the first bubble column, and then the spike of bromate occurs in the third bubble column. Then we have again a little bromate formation in downstream, and since there is no ozone residual downstream in the other bubble columns, the effluent concentration stay constant, and now it is equal to 14 micrograms per liter. Now let's do another try and split the dose across 3 bubble columns. So again, we are dosing the same amount of ozone, but in this time we are dosing in the first bubble column, 33% of the dose in the first one, 33 in BC3, and 33 in BC5. So let's see what will be the effect on bromate formation. Okay, we are almost okay, we are there. Now we can see that the highest ozone residual occurs in BC5, again close to the diffuser. There is some ozone residual in BC3 and in BC1, but let's see what happens to the bromate. So the bromate formation in BC1 is now very limited, it's only 0.6 microgram per liter. Then we have a small jump up in BC3 to 3 micrograms per liter, and the highest formation occurs in BC5, in the last column where we are dosing. But in the effluent, now we have almost 12 micrograms per liter. So summarizing a bit, in the first simulation, we dosed everything in the first bubble column and we got 16.8 micrograms per liter. In the second simulation, we dosed 50% of the gas fluoride in the first one and 50% in the third one. And we got a concentration of bromate equal to 14.3. And now we split the dose across 3 bubble columns and we got an effluent bromate of 12. So just changing how we introduce bromate in our system, in our installation, can help to lower the bromate formation to 30%. So thanks, Wim. We can go back to the slide.
Perfect. Thanks, Roberta. Yeah, I also want to congratulate my colleagues for the braveness doing live simulations. We could have recorded everything here. And as people working with live demos know, yeah, it's always a challenge. You have to do it in front of a live audience. So thanks for the guts, for having the guts for that. So let's go to the conclusions of this section. There are 4 take homes here. The first one is the removal of target contaminants is actually much less. It should be much less. There is a typo here. Much less affected by your ozone introduction strategy compared to your bromate formation. So you can have similar removals of your target contaminants with splitting doses, but you can have very different bromate formations. There can be some differences in the target contaminants as well, but we are talking about like 1-2% or so. So it's very subtle, very small differences. Actually, you can design plants for minimal bromate formation by spreading the dose. But of course, I have to go to the third point. I think our team actually thinks, working with all these different plants, drinking water, wastewater, some are industrial water. It really depends on the matrix a bit, how your ideal plant would look like. And there can be some subtle differences that can have huge impact because it all depends on your matrix and how your local ozone, so not the overall ozone, but your local ozone builds up in the system. We believe, for example, if you look at two extremes, drinking water ozonation systems where you need a residual, you need a CT, and when you look at, for example, systems for micropollutant removal in effluent, probably these systems should look very, very differently, or they can at least look very differently because the concept is completely different. In fact, there is also a lot to do, as we as practitioners know, about, well, side stream versus bubble column. Yes, there are differences in costs, in maintenance, pros and cons for each, but there are differences potentially in bromate formation as well. I'm not saying that side stream is inherently leading to higher bromate formation. There are side stream systems out there that produce very limited bromate. But in fact, if you talk about keep the HRT in the side stream short, because that's the general guidance, if that is too long, your bromate goes up very, very fast. Well, actually, you are saying do not allow all ozone to dissolve in the side stream. Because if that would happen, you go very, very similar to this first column Roberta showed, which is the more drastic case of a very, very fast transfer of your ozone in the water. So it has to do with the amount of uptake of your water locally, and also the amount of local transfer efficiency you have. This will, in the end, determine your final ozone residual, and your final ozone residual then leads to your local bromate.